Okay, so hello everyone. I'm Nadav from Autotalks. My original plans were to have this talk in person, but unfortunately I had to change my plans. So thank you for adjusting your schedule and joining this talk in its updated time slot. I'm super excited to be here. It's a real honor for me to speak at ZTS and take an active part in the Zephyr community. I would like to share with you today the journey we had in the last 2 years developing a SoC from scratch using Zephyr. Just a second. Yes, okay. Okay, so we will start with a short introduction, so you will have some background about the SoC as a product. Then we will talk about the SoC bootflow, the pre-silicon development phase, and list some additional features and challenges we had along the way. We will wrap up with a summary and some time for questions. Here is a list of terminology and abbreviation that I'm going to use during this talk. So SoC, System on a Chip, V2X, Vehicle to Everything, AP for Application Processor, EHSM for Embedded Hardware Security Module, SDR for Software Defined Radio, BL for bootloader, I or DCCM for instruction or data closely coupled memory that we have per AP core, and CSM, which is cluster shared memory, which is shared between the AP cores. Okay, so a little bit about me. I have a bachelor degree in companies and joined Autotalks about 7 years ago. After about 2 years, I was offered the position of a software team leader. Today, I'm the software platform team leader, which develops the low-level code in our software hierarchy. The software platform team was the first team to shift from Autotalks Gen 2 to Gen 3 Zephyr-based SoC, developing the software parts in parallel to the SoC silicon development by the VLSI team. A little bit about Autotalks. Autotalks is not a typical startup company. It is almost 16 years old. It was founded in the early days of standardizing V2X technology. Autotalks is a multidisciplinary company with R&D teams in the fields of software, hardware, VLSI, RF, and algorithms. The vision of Autotalks is to have a world with no accident. Our mission is to develop the best V2X solution for the market needs. In Autotalks, we developed a V2X system on a chip. Autotalks' first product was FPGA-based and was aiming small-scale deployments, such as vehicles inside mines, where the number of vehicles is relatively small, but the vehicles are physically big. Having an accident inside a mine can be an expensive event. Our Gen 2 product was developed in cooperation with ST Microelectronics. It is ARM-based and runs Linux or ThreadX, depends on the selected architecture. It is already deployed in some regional projects, such as the European Sea Roads project, where it is deployed inside roadside units along the road. In another project in the US, it was deployed in the emergency vehicles and traffic lights in order to provide traffic lights priority to emergency vehicles on the way in cases of emergency. Switching the traffic light to green for the emergency vehicle to pass with minimal delays. It was also selected for several mass production OEM projects and will soon hit the roads. Our Gen 3 product, which is our focus here, is in an ongoing development. It was developed from scratch by our talented VLSI design and verification engineers. It is Synopsys ARC-based and runs Zephyr all along its bootflow, from its ROM to the V2X application. It was already selected to future deployment projects, including infrastructure, cars, and bikes. It was designed to have high performance and throughput to support advanced V2X use cases. Our SoC provides the very low access layer of the V2X stack. In some architecture, it also runs the V2X stack software itself up to the application layer. A little bit more about our Gen 3 Tecton SoC. It contains a dual-core Synopsys Arc HS48 application processor, a RISC-V core for the embedded hardware security module, and 3 CIVA DSP cores for the SDR. It has several peripheral interfaces such as UART, SDIO, Ethernet, SPI, QSPR for NOR and NAND flashes, a JTAG interface for debugging, Hyperbus interface for HyperRAM, and more. Internally, it has several memories, several crypto engines, and some proprietary IPs such as mailboxes and hardware semaphores for inter-process communication, timers, firewalls, and more. A little bit about V2X. V2X stands for Vehicle to Everything, with the main goal of preventing accidents and save lives. There are two standardized V2X technologies. One is DSRC, which is based on Wi-Fi 802.11 standard. The second is called CV2X and is cellular-based and uses direct link between the communicating parties. Our chip is the only V2X solution that supports both of the technologies. V2X as a radio-based sensor is the only non-line-of-sight sensor. It can identify a car bursting into an intersection on a red light, even if it is behind the corner or relatively far for a visual sensor to detect. In this picture, you can see several examples of V2X communication channels. V2X can be installed in vehicles, including motorcycles. It can be installed in infrastructure, such as traffic lights or roadside units along a highway. It can also be installed in vulnerable road users, such as bikes and scooters. There is currently no hardware V2X solution for pedestrians, but they can also be protected, for example, by integrating V2X with a camera, which can give V2X indication to drivers when pedestrians are in danger. In this picture, you can see some common V2X use cases, such as do not pass warning or intersection movement assist. Since V2X is not our focus, I just want to give you a glimpse of it. The fastest and most intuitive way will be to show you some short videos. In this video, you can see the orange car turning left, the blue car approaching the intersection, but the driver can't see the orange car because of the car in the other lane. V2X as a non-line-of-sight sensor would detect the incoming collision and alert the drivers. This video is an example of a roadwork warning use case. The driver is not aware of the roadwork in front of him. When he does, it is too late to prevent a collision. In this case, roadside unit installed along roads or even just on the roadwork infrastructure itself could have alerted the driver in advance. I saved you the 2 last seconds when it really crashes. Okay, so this was the introduction, and now we will focus on the Tecton SoC, the SoC development. We will start with the SoC bootflow. The SoC bootflow starts from bootloader 0 of the application processor and EHSM cores. Both are implemented in ROM, in read-only memory. The application processor bootloader 0 sets the minimal must-have SoC configurations, such as clocks and resets, and continues by loading bootloader 1 of the AP and the EHSM firmware. Bootloader 1 expands the SoC configuration by initializing additional memories and drivers, initializing the SDR cores, and loading its firmware, and finish up by loading and executing the V2X application image. The V2X application image is where the V2X logic is implemented, communicated with both the SDR cores, the EHSM, and the external host using the V2X SDK. We will focus on the application processor, which is Synopsys Arc-based. Perhaps the trivial way would be to implement bootloader 0 as bare metal. By doing so, we would have full control over the software flow. No additional thread or OS scheduling was involved. What you code is what you get. Bootloader 1 could have been implemented as MCU boot, which is part of MCU manager. MCU boot is a secure bootloader tool which is supported by Zephyr and is commonly used and tested. This way, we were leaving only the V2X application to be Zephyr-based. The path we took is a little bit different. When designing the SoC bootflow in light of the system requirements, we have decided to implement the whole SoC bootflow as Zephyr-based. This allows us to utilize the drivers existing in Zephyr, which are used by bootloader 0, bootloader 1, and the application. It also allows to implement the image loading related code and boot related function as libraries, such that both bootloaders can link with them. Although MCU boot supports secure boot, our secure boot design is very different and can be easily implemented based on MCU boot. Also, MCU boot does not support all the boot interfaces in our system requirements, which include UART, SDIO, Ethernet, and more. Why did we choose to develop our Gen 3 SoC using Zephyr? As I said before, our Gen 2 SoC was Linux-based. Our developers are already well familiar with Linux concepts such as device tree and kconfigs, which are also present in Zephyr. Zephyr is a rich environment in terms of supported drivers, features, the Z-test environment, and more. Z-test is modular and highly configurable OS. We saw that we can use it all along the boot flow, each stage of the boot flow with its own configuration and footprint limitation. We also conducted some benchmark of context switch and other OS-related functionalities and found that Zephyr is the best choice for our demanding performance requirements. Zephyr is an open source project. There are no secrets or behind-the-scenes functionalities. Also, there is a growing community and places to be looking for answers, such as GitHub, the Zephyr mailing list, and Discord. Also, Synopsys is one of the initiators of the Zephyr project. It has contributors of its own and can support us if needed. A little bit about the source tree structure that we used. Zephyr published an example application repository to be used as a reference of how to develop Zephyr-based applications. In this example, the Zephyr source tree is being expanded by adding out-of-tree applications, drivers, libraries, and so on. We like the concept of having Zephyr modules, being able to keep the Zephyr OS code tree clean and add all of our SoC additions in a dedicated repository. We have 3 software teams. Each implements a different layer in our software solution. We wanted to be able to separate the development into several repositories. Each handles its own logic. One of them is used to expand the Zephyr OS tree with our SoC, boards, drivers, and any non-V2X related code. Another one contains all the V2X specific logic, such as libraries, high-level drivers, V2X SDK, and more. When needed, we added or modified code in Zephyr OS repository itself under a dedicated ifdef for easy identification of our modifications. This assists us when upgrading Zephyr to a newer version. We can keep track of our additions and make sure they still hold for the new version. An example of such an addition is in the arc-reset.s core file. We needed to add SoC configuration in the very early boot stages, such as PLL configurations and hardware deassertions. Okay, let's talk about the pre-silicon development phase. The pre-silicon development phase is very challenging. The hardware is not there for you to develop your software. The hardware itself is also under development, so when something is not working as expected, the issue can be either in hardware or software. In the pre-silicon development stage, we had several development environments to work with. Each has its own pros and cons. We had a hardware emulator, which is slower than the real SoC, but quicker than the hardware simulator. It supports some peripheral interfaces such as UART and Ethernet, unlike the pure software simulator. Its main disadvantage is that it is not fully emulating the real SoC, meaning that code that configures the clocks is not being tested, or since it's not sensitive to uninitialized Z values, it will not detect related bugs. The hardware simulator is very slow. Simulating 1 millisecond of execution takes about 1 hour. Simulation of our bootflow, where several images are being loaded, can take between several hours to days. It doesn't have peripheral interfaces, but it is sensitive to clock configuration and Z values, which make it more real SoC accurate. Both the hardware and software simulators allows view into the SoC digital waves and a JTAG interface for debugging. The software simulator is much faster. It runs on x86, allows quick debug cycles, but it is not simulating any hardware, so it can be used only for pure software debugging. Here is a screenshot taken from the hardware simulator. The hardware emulator gives the same view. We can see here, for example, the digital waves of the QSPI lines, which are connected to QSPI NOR flash. We can also see the CPU clock, the CPU PC register, and more. This allows us to debug complex bugs, which are hard or impossible to debug using JTAG. Sometimes when the VLSI team is chasing a bug, the software is just a tool for tracking down the root cause of the hardware bug. Using the digital waves, we can figure out if the issue is with one of the QSPI lines, if it's a bus error, or if it's something with the command being sent from the QSPI controller to the flash. We can also know what is the PC register value when the issue occurs. Using the code disassembly, we can figure out which function is the one triggering the issue. I will show some additional SoC features that we developed. Secure bootflow. As I said before, our SoC integrates an embedded hardware security module, or EHSM in short. The EHSM is the root of trust of the system. It has the ability to authenticate, sign, and decrypt the images being loaded along the boot flow. In this diagram, we can see the boot flow over time. The SoC boot flow starts from bootloader 0 of the AP and the EHSM cores implemented in ROM. The EHSM allows loading the EHSM firmware only, as seen in the green line. The motivation is to keep the EHSM bootloader 0 logic to the minimum and expand the EHSM abilities in a loadable and changeable EHSM firmware, which allows loading all the rest of the images as seen in the blue lines. Every image being loaded by the AP bootloader 0 or bootloader 1 is being passed through the EHSM. Only after a successful authentication and decryption, this image will be processed by the AP core. Switching between the AP images is done by either a reset or a direct jump to the next image. Another feature that we implemented is the ability to utilize high-performance instruction memory implemented in ROM, in a read-only memory. In our SoC, we have several memories. The memory with the highest performance is the ICCM, the instruction closely coupled memory. We have both ICCM RAM and ICCM ROM. Bootloader 0, for example, is implemented as ICCM ROM. We have some ICCM RAM space, but it would be nice to have some more. The chip designers didn't like the idea of adding some more RAM, but ROM is cheaper in terms of silicon area, so it was suggested as an alternative. As you can see, 1 megabyte of RAM and 3.5 megabyte of ROM equals the same silicon area. How can we utilize the ICCM ROM? We can put in there pieces of code that do not tend to be changed. and are also frequently used. For example, we have implemented in assembly a very efficient memset and memcopy functions. Those are relatively simple functions, which do not tend to be changed and are frequently used. Another benefit in the reduction is reduction of cache pollution. Since the ICCM ROM is not cached, if, for example, we are running our application code from the CSM, the cluster shared memory, which is behind cached, and the cache is already full, calling uncached function will cause some cache lines to be invalidated. Instead, if we frequently use functions are Instead, if the frequently used functions are in a non-cached memory, such as ICCM ROM, it will not affect the cache and can sense some cache misses. Here you can see an example of the symbol table of the code that goes into the ICCM ROM. All the functions are defined as weak functions, such that they can be overridden by the application that links it. There are several test functions that can be used for debugging and testing the ability of overriding weak functions. There are also the memset and memcopy functions implemented in several variations to be most efficient. For example, memcopy of a dword aligned source or destination can be implemented very efficiently without the need of taking care of alignment or fringes. The best way we have found to implement it using the ArcMetaware toolchain is to compile the ICCM ROM content as ELF file. In the CMake of the application, we added the Zephyr LD options command, which tells the linker that there are additional symbols to be linked with. This allows the application to call those functions, even though the functions are not compiled as part of the application itself, but present in the ICCM ROM. Here you can see a made-up example application code. The function oprom atlac memcopy is implemented as part of the application, such that it overrides the one placed in the ICCM ROM. Using the ability, we can replace the ICCM ROM functions in case a bug was found or if the function logic should be updated for a reason. Calling the memset application will trigger execution from the fast ICCM ROM. Calling the memcopy function will trigger execution from the locally implemented memcopy function. Another feature that we implemented is to utilize high-performance memories to contain frequently used code and data. We have several memories available internally and externally from our SoC, with varying performance. Some are behind L1 cache, L2 cache, or not cached at all. The IND CCM, for example, the instruction and data closely coupled memory, are the fastest, uncached and also uncached memories. The HyperRAM is the slowest and is L2 cached. The code contains functions which are rarely used, such as initialization functions being called only once at any time. On the other hand, there are frequently used code, such as the V2X RxPath code, which can get rates of 4K packets per second. The V2X TXPath code is in between, with rate of 10 packets per second on average. The frequently used code and data can be placed in a relatively high-performance memory. This is a future feature. We did not start its detailed design or implementation. We can assume that we will have to do some linkage magic here in order to map functions to specific sections, depending on the function usage and memory performance. This will allow us to improve the overall performance of our SoC and support the demanding throughputs of advanced V2X use cases. Okay, let me detail some bugs and challenges that we had along the way. Okay, so the Zephyr Arc reset and start bug. This bug was found when we moved from using the hardware emulator to the hardware simulator. Code that ran with no issues on the hardware emulator got stuck in very early reset stages on the hardware simulator. As noted before, the hardware emulator is not sensitive to Z values. Z values can happen, for example, when the hardware has no defined reset value and the software is not taking care of setting any init value. When we discovered this issue, we started debugging it using the digital waves, first with our VLSI team and later with Synopsys support. In the debug session, we have found that the arc reset and start function is missing code that initializes all the arc core registers, R0, R1, R2. Synopsys is an active partner in the Zephyr community and has several contributors who confirm the issue and push the fix into the Zephyr codebase. Another bug is Synopsys arc cache invalidation bug that we have found. As described earlier, we have several memories in our SoC. Some of the memories are behind L1 cache and some are behind L2 cache. The Synopsys Arc CPU subsystem provides a way to control the caches, for example, to lock cache line such that they will not be spontaneously invalidated, flush or invalidate the whole cache, or a specific region of the cache. While developing a unit test that stresses the memories by reading, writing, and verifying the data, we encountered an issue where at some scenarios the data being verified is not as expected. Our test was developed to a random accesses at random addresses, alignment, and size. While debugging the issue, we found out that the issue occurs when the data is inside a single cache line, meaning that it's smaller than a cache line, and both the start and end addresses are within a single cache line. We added Synopsys support to our debugging efforts. After validating that we are using the cache APIs correctly, they checked their hardware side implementation and found out that there is indeed a bug in the API. In case the range is within a single cache line, the operation is being translated to 0 lines to be invalidated, and hence the data remains valid in the cache. Later on, Synopsys publicly announced the bug with a fixed version. This example is not a bug, but a software challenge that we had to deal with. In the Synopsys Arc memories architecture, there is an option to have a shared memory area that can be either cluster shared memory or L2 cache. For example, 2 MB of shared memory can be defined by software to be either 2 MB of CSM, 2 MB of L2 cache, or split between CSM and L2 cache. The challenge here was that the shared memory reset default is L2 cache. During our bootflow, we use the CSM as the destination memory for our images. Our secure bootflow requires us to have a CPU reset in between images, but the memory region where the image is placed at becomes L2 cache and the image can be executed. Luckily, we have a small private CSM, which is not part of the shared memory, and it is always CSM, even after reset. The solution was to link the image such that the reset and start function and other early stage code that is executed before configuring the shared memory as CSM is linked to the private CSM memory. Okay, let's summarize. Okay, so Tecton SoC, the Tecton SoC was developed from scratch using Zephyr. Zephyr runs all through our bootflow, from the ROM to the application. We already had 2 SoC tapeouts. The third is expected in the next few days. Our first official version with a real SDR is about to be released soon. And when deployed, Zephyr will be in the core of a life-saving product. That's it from my side. So if you have any questions, this is the time.
Does anybody have any questions? think we're good.
Okay. So thank you for joining this talk.
Thank you.
If you have any additional questions, you're welcome to contact me on Discord.